Hello again and welcome to Lesson 7 of the GPS course. This time we'll be talking about GPS surveying techniques. We'll have several topics, including continuously operating reference stations, real-time kinematic, DGPS, and many other similar subjects. The first topic we'll be discussing will be static GPS control surveying. This is where the GPS receiver is motionless for a time, usually a relatively long occupation. If it's planned correctly, a GPS static survey can be independent of some of the things that have plagued such work in the past, meaning weather conditions and various other problems. However, still, there are some things that need to be considered. Overhead obstructions, access between points, and so on. As I say here, there's seldom anything that is more expensive in a GPS project than a surprise. It's worth noting that the standards that governed control surveying in the past have been upgraded. The Federal Geodetic Control Committee has issued new standards. It used to be that there were first, second, and third order standards, first being the highest at 1 part in 100,000. However, now all of the old first, second, and third order standards are now under a rubric known as C, and the FGCC has proposed new standards B, A, and AA. These are 100 or 10, 100, and 1,000 times more accurate than the old first order. GPS, in other words, has really upped the stakes in terms of accuracy standards according to the federal government. It is now relatively easy to do GPS surveying, that is when everything works the way it's supposed to. So the now C grouping of accuracy can be done without too much planning. However, if there are going to be troubles like access to the points, overhead obstructions as in trees, or if, for example, something like helicopter access is required, obviously planning needs to be part of the process. One of the things that is very useful is understanding the existing control that is currently available. We discussed last time the fact that many brass tablets, brass caps, have been set around the United States by the National Geodetic Survey. And online, under the website seen here, one can retrieve sheets that are similar to what you see on the right-hand side of this slide. These sheets have a great deal of excellent information concerning the coordinates, the quality, and many of the details about existing control points that can be used as checkpoints in any GPS survey. Of course, the first retrieval date at the top of the sheet is valuable to know when the point was last recovered. And then there's the point identification number. You see that 2 uppercase letters followed by 4 numbers. The latitude and longitude in this case, NAD 83, is followed by the particular adjustment. In this case it's 1992. And then the vertical value, NAVD 88, in meters and in feet. In this case it was by a GPS observation. There's much more detail here. I'll leave it to you to read, but suffice it to say, for the objective here, the NGS datasheet is helpful to learn what control is available in a particular area. Further on down this particular sheet, you see the state plane coordinates indicated by SPC. We talked about plane coordinates last lesson. Also the UTM coordinates, and now these will be familiar, northing, easting, of course the units, the factor, the scale factor, followed by the convergence. And Also, at the very bottom of the page is the calculation of the combined factor for this particular station. It's worthwhile to note that also an NGS datasheet has information on how to reach the station on the ground, which is of course useful if you're going to use it for control for any GPS surveying. Having said this, of course, these days it is quite possible to not have to occupy an existing brass tablet, brass cap, such as indicated on this NGS datasheet. The reason for this is because of the continuously operating reference stations that have been established by the National Geodetic Survey. They're very useful. These active stations are a network, and of course the most straightforward benefit is that a user can do relative positioning without operating his own base station, and by depending on the CORS station, which, as you see in this slide, downloads its reference information from tracking the GPS network to an archived base station that is available on the internet. You can access this and then combine it with the GPS data that you have collected and post-process for a differential position, a relative position, without having to occupy an existing control point on the ground. Now, the United States is by no means the only place in which such a network exists. I mention here the network in Japan, the GeoNet, which was established by GSI in the aftermath of the Kobe earthquake. And also, we've talked before about the International Terrestrial Reference System created around the world. This is available from the IGS, International GNSS service. And so the point here is that while there is a continuously operating reference station network in the United States and in North America, that is not the only place in the world where it is available. Also, it's worth noting that regional continuously operating reference stations are available. Here is the Southern California Integrated GPS Network, which is run by a government university partnership. And more of these networks are appearing across the United States, sometimes on a statewide basis, county basis, and other regional designations. These continuously operating stations occupy a known position and then track the full constellation of GPS satellites continuously. Then this data is made available, sometimes with a subscription cost, but in the case of NGS for free, and it is available then to do differential positioning using a roving GPS receiver. Now here we have the United States CORS network operated by NGS. It's quite valuable. We can take advantage of this from the NGS website. Continental NGS has two components, the cooperative CORS and the national CORS. Together they comprise a network of hundreds of stations constantly logging GPS data, and the data is available in the receiver independent exchange format, or RINEX format. The reason for this is the RINEX format allows you to use any type of a receiver that is logging post-processable data to work with. This RINEX is available from virtually every kind of standard GPS receiver. NGS manages the national CORS to support this post-processing, and there I give you the website where you can see where this is available. And both code and carrier phase are available throughout the United States. And here is a look at that website. At least a portion of it. The cooperative CORS supplements the national CORS. And the reason for this cooperative arrangement is these sorts of organizations, which as you see are universities and others, work cooperatively with the NGS to provide the stations that we all can use, in almost all cases free of charge on this system. Now, last time we talked about the North American datum 1983. We talked about the ITRF00, and we discussed those datums and their relationship. And I believe I pointed out that the CORS stations available across the United States can be had in either datum, which is a very useful thing. In other words, one can have it in NAD83 according to what is typical in North America, or also compute in the International Terrestrial Reference Frame, which is obviously an international standard. Now here is just a very brief look and an address of a site known as the Horizontal Time Dependent Positioning website. The function of this website is to allow you to move a station in time from one epoch to another. Fortunately, in the case of NAD83, that is usually unnecessary, but if it is necessary, this website will help you do it. Now, caution, if you are using the continuously operating reference stations, you need to be careful that the ARP value, the antenna reference point value that will be given on the website, is speaking of usually the bottom of the mount as indicated by this diagram. And then there's a height above the ARP, above the antenna reference point, to get to the phase center of the antenna, which of course is where you want to be for an accurate position. Now, some post-processing software, notably Trimble's Geomatics Office, have canned values to get from the antenna reference point up to the phase center, depending on the make of antenna you're using. However, it's useful to know that NGS provides the same information available on this website, where you can, as you see, look at the particular antenna you're using and learn the offset that you would need to apply to go from the ARP up to the phase center. And there's more. The NGS also provides information on precise orbits. Now, the point here is, as we discussed, the broadcast ephemeris that's available in the navigation message of GPS has its difficulties in that it is a bit delayed from when it was last uploaded by the control segment. So, obviously, if one is post-processing, it's very useful to have the latest precise orbit information, or the precise ephemeris information of the satellites that you're observing. In other words, it would be best to know the ephemeris at the moment that you are actually observing the satellites. The information directly from the tracking station, and that information is available. Here is a website again that shows you how you can download the orbital information for the time that you were observing the satellites. This clearly can eliminate a good deal of the ephemeris error from a position. And not only is such information available for the network in the United States, it's also available for these international networks that we've discussed. In other words, precise ephemeris data is available from the IGS tracking network, and here you see a graphic of its extent. It's virtually worldwide. And of course, one can also download the tracking information from these antennas, these known positions, and use a roving GPS antenna and post-process against these CORS stations internationally to do differential positioning, relative GPS positioning. And yet another website where the IGS data is available. The SOPAC site, the Scripps Orbit and Permanent Array Center, from here you can also download the data from stations around the world. Very useful. All right, this is good to know this, but let's suppose, stepping back a moment, that it's necessary to establish your own control for a county or a region or a project with static GPS occupations. In other words, it's necessary to design a static network in which you can create your own control to work from. Now, of course, in the past, when this was done optically, and here we see some surveyors on a Bilby tower high above the Ozark Mountains in Missouri, these observations were done at night with lights and angles turned through triangulation to establish horizontal control. This, of course, is no longer the way it's done. We now do it with GPS, but it's hardly surprising that at the time they were doing the work in this way, they weren't terribly concerned with the sky visibility. They were concerned with getting high enough over obstructions to see the other stations. Now, one good idea if you're designing a control network is to divide the area that you're going to control into quadrants. Here you see that done. Now, in this case, the horizontal control stations are triangles, the vertical control stations are squares, and the project points are red dots. Now, in vertical control, it's a good idea to have one in each quadrant and one in the middle. And horizontal control, as you see here, we have one in each quadrant for horizontal control. And on the right, you see the FGCC standards for the various categories of control accuracy. And then, of course, in the design, the project points are indicated. These are the points on which a control is going to be required. These are the points that are going to be coordinated based upon the control available around them. Well, once the network is fundamentally laid out, not quite designed yet, one of the things that needs to be evaluated is the access to the points. Obviously, difficulty getting from place to place to occupy these is going to be an issue, since in a static GPS survey, the control points and the points to be coordinated, the project points, need to be occupied simultaneously. They need to observe the same constellation of satellites at the same time. So it's important to be able to be on the station, ready to observe when the sessions begin, simultaneously on control and project points. So access is an issue. Also, it can happen that a point that requires control is in an obstructed situation, trees, buildings, other problems. So it's important to plan movement or an offset of this point from an area that will not be capable of being observed with GPS to one that will. And this sometimes requires a bit of conventional surveying to move it out from under the obstructions, so that it can be coordinated there, and then the offset used to bring the coordinate back to the obstructed position. Also, it can happen that a point needs to have an azimuth mark, meaning there needs to be a place that one can occupy with a conventional instrument, an optical instrument, backsight, or establish a known azimuth, and then turn angles to be able to tie in other features. These azimuth marks need to be planned and can be done in various ways. One, of course, is astronomic observation. And, of course, another consideration making a plan is permission. Private landowners, government officials, etc. Need to be consulted before the actual observations are conducted, so that you don't find yourself stopped unexpectedly in the middle of a plan. Well, getting around is an issue, and permissions and so on, but also consideration of what the constellation is doing must be taken into account. Of course, the satellites need to be available, they need to be visible, and they need to be visible, the same satellites need to be visible at both ends of the vectors that are going to be occupied. So, luckily, most GPS software packages allow you to know how many satellites are above a horizon at a particular location. And of course, the position dilution of precision is something that needs to be taken into account in a static GPS survey design. And here we have some charts that indicate how that can be evaluated in some cases. You see here the number of satellites on the left, and on the right we see the position dilution of precision. It spikes, of course, when the satellites drop. When some set and we have only 4, those are the 2 red areas. And of course, when that happens, the PDOP goes way up, because of course the geometry of the satellites from the receiver's point of view is not optimal. There are some other spikes too as the satellites move from one configuration to another. Obviously, it is not wise to do GPS observations when the PDOP is high. One needs to be aware of those times so that in planning the observation schedule, when you're going to occupy the points, you're not trying to measure a baseline when the PDOP is spiking. Here's another graph that can be available in software packages. This shows a polar plot, which satellites are above a particular mask angle. In this case, it's 15 degrees, and it shows what the tracks of the satellites would look like if one was looking straight up at zenith. And yet another graph. This time the time is shown on the left-hand column, and then the elevation and azimuth of individual satellites or space vehicles, SVs, are shown. This is all in view, all above a particular mask angle horizon, and you can see how that changes over time. And one could use this to plan particular observation windows. When 4 or more satellites were up, the PDOP over there on the far right was at an acceptable level. These all seem to be fairly good. And then one can plan the periods that you'll be observing from particular stations. There are some details here concerning how it would be possible to make the most of this set of data concerning the constellation. But obviously, movement between stations needs to be considered. Optimal PDOP, in other words, low PDOP, needs to be considered. And, of course, more than 4 satellites in planning the observation schedule. Now, the observation schedule means when a receiver is being occupied on a point and when it needs to be picked up and moved to another. Remember, with a static survey, the receivers need to be on point simultaneously. In planning the survey, it's always useful to note that the ionospheric error is smaller after sundown. Now, it used to be that we did a good deal of observing at night. While it's less convenient in many ways, it's worth knowing that the ionospheric error is less when the sun is down. Now, in this chart, presume that 740 to 830 is a reasonable window of good constellation of satellites, and for the most part, a good low PDOP. Of course, dividing that window up into segments would depend on how long the baselines were that needed to be observed. Obviously, a receiver at each end of each baseline. Of course, the longer the baseline, the longer the occupation. And then, of course, the other aspects we've talked about. How long does it take to get from station to station? These are considerations in designing the survey. Here's a layout that shows basically what we had before in terms of project points, a horizontal control and vertical control. A good rule of thumb, if one is doing your own control survey, is to observe the accepted control points first, and to find out if there's any difficulty with the published coordinates. So let's suppose that these are NGS brass caps. To learn if there's any difficulty with the published coordinates on these control stations. So observing the baselines between them is good practice. Okay, now, first of all, it's worthwhile to note that in naming sessions in a static GPS survey, Julian days are common practice. And that means, in GPS generally, that the Julian days are counted consecutively from the 1st of January of any given year. In this particular case, we're talking about Julian day of 49. Secondly, it's worthwhile talking about dependent and independent vectors. In this case, we're using 4 GPS receivers which are occupied simultaneously on 1, 3, 8, and 13 point numbers. You see 3 lines in blue drawn between them, and then there are 3 lines that aren't drawn. The independent lines are the, generally speaking, shortest lines, and the trivial lines are the longer of the 6 that are created using 4 receivers. Now, it can't be said that always the shortest lines are called the independent vectors, but it can be said that if you have 4 receivers, you have 3 independent lines. The number of receivers being r minus 1, 3 lines. Might be worthwhile to talk a little bit about why one does it this way. It can't be said that the shortest lines are always chosen as the independent lines, but generally speaking, that's the case. The distinction between independent and trivial lines involves the concept of error of closure, or also known as loop closure. Loop closure is a procedure by which the internal consistency of the GPS network is discovered. A series of baseline vectors, like you see here in the blue lines, for more than one GPS session is formed into a loop. And this closed figure can be evaluated to see if there's an error of closure. Now, obviously, if one were to take vectors that were just from one GPS observation period, one session, the error of closure would be 0. And that wouldn't evaluate anything. However, if, let's say, the line between 13 and 1 was established from a different session than the other 3 lines of this 1, 3, 8, and 13 figure, then one has a way to evaluate to some extent the veracity of the observations. So the error of closure is an intimate part of this concept of distinction between independent lines and trivial lines in a static GPS survey. Another concept that's important in control work with GPS is redundancy. Now, redundancy refers to several things, but one way to think of it is if a station is occupied more than once in the conduct of a survey. If it's occupied more than once, several good things happen. It's recentered over the point more than once. Its height is recorded more than once. And obviously, baselines or vectors come into the point from other stations other than the ones originally located. Redundancy, in other words, being measured more than once, is a useful thing in trying to evaluate the accuracy or the correctness of a network. Again, the Federal Geodetic Control Commission has standards for redundancy, which are listed here, and the repeat measurements of independent baselines provide a useful tool for determining the correctness of the ultimate network, the ultimate control network that is established using GPS static surveying. Now here we have a design that shows in different colors of the lines the occupations using 4 GPS receivers and how they are used through simultaneous occupation on these stations to create a network. And here you have the session numbers, the independent and trivial lines listed. The A, B, C, and D receivers are shown and what points they occupy at what stages. This is obviously done over 10 sessions, over 2 days, 2 consecutive days, and there's a good deal of redundancy in the network. However, that's simply the design. That doesn't mean that that's what will actually occur. Now, the NGS has provided a very useful formula, which is listed here, for calculating, using some safety factors, how many sessions will actually be required to do this particular project or any project of this type. And you see all the variables there, and they're discussed here as to what they stand for. At this point, I would just like to point out that since, as you know, the number of sessions expected for this was 10, I wonder if this calculation tells us that we'll actually do the work with 10. Turns out that, of course, part of the variables here is one could state the amount of redundancy that you want to have in the network. In this particular case, N was used at 2.857 for this plan, this design. A safety factor of 0.1 was included, and a production factor of 1.1 was used. Well, it turns out that the number of sessions based on this calculation is 14 rather than 10. Of course, the lesson here is simply that the plan presumes everything goes perfectly and that there are no difficulties. Of course, that won't happen. This formula just allows you to put in a safety factor. If one was going to plan how long it was actually going to take, it would be better to say that instead of 2 days of work using 4 receivers, it might actually take 3, just to be safe. This, of course, means that perhaps one of the receivers doesn't make it to station on time, and that line has to be redone. Perhaps permissions that were once given are retracted. Perhaps weather creates delays in terms of getting from place to place, and other unexpected occurrences. Okay, well, that's a bit of discussion about static surveying, but as you know, a good deal of GPS these days is done not static, but with DGPS or real-time kinematic, RTK. In other words, the CORS discussion that we had earlier over here on the left, let's suppose that there's a base station that exists on a building, an RF tower, or actually even a geosynchronous satellite. And those are operating to give real-time corrections to a roving GPS receiver. Or it can be done post-process, as we discussed with the CORS stations. But in any case, in the case on the left, the user doesn't have their own base. In the case on the right, real-time kinematic, the user may have their own base set up on a control point, but again, operating in real time. However, one thing you notice about these real-time corrections is that the base station in both cases would be at a known point, whether it was on a building permanently or it's on a tripod base station used by the user, would be set up over a known point. This allows the base station to produce corrections based upon its fact that it knows where it is. The constellation is telling the base station that it is in a slightly different place, so corrections can be created to beam to the user who is at the unknown point and apply those corrections in real time, and therefore you can have a real-time position at the unknown point. This is the fundamental concept in both DGPS and RTK. However, one thing you notice about this approach is it's radial, meaning that you have a known point in the middle, the base, and then the unknown points around it. Obviously, this gives little geometric solidity, because clearly if there's an error in one of these radial baselines, it would be tough to catch it. because there's no real redundancy. This picture here is indicating two receivers, A and B, and it's possible by double occupation, one receiver going one way and the other going the other, by double occupying the unknown points to get some redundancy and some checks against the positions from a base. Another way to do it is to use one receiver, and instead of double occupying with two different ones, one receiver with a certain amount of time, let's say 4 to 8 hours between the first occupation and the second occupation on the point. Another way, obviously, is to move the base to another known point. Obviously then, if you have vectors from another base into these points, you have a check. And this is one of the things you need to consider in doing a GPS real-time survey, is that radial vectors provide no redundancy or check unless double occupation or two bases. Now, of course, one of the advantages of a continuously operating reference station network is that since those bases are operating simultaneously and all the time, it's possible to download the positions from more than one base and process your new position based on these continuously operating reference stations and have some redundancy. DGPS is a term most often used for this kind of arrangement with pseudo-ranges or code phase, as we discussed earlier. This is not a carrier solution, but again a code solution, probably a CA code solution. Now, it's possible to do sub-meter work, plus or minus a meter or less, tracking 4 satellites minimum with an Rtcm correction. This means that the rover, as you see, has basically a radio receiver that can receive these correction signals being transmitted from the base. Simultaneously, of course, it observes the same constellation of satellites as being observed at the base, and the microcomputer on the receiver allows immediate calculation of the real-time position. Now, that radio receiver can today be a cell phone. It's more and more used for this kind of arrangement. Of course, it doesn't have to be real-time. You could do this same arrangement and not collect the correction and do post-processing. Just a word about the correction signal. This Rtcm is named for the Radio Technical Commission for Maritime Services, and then Special Committee SC 104. They created a standard some time ago, in 1985, and there's been some work on that standard in recent years, but it's still a fairly common format for the correction signal that goes from the base station to the roving GPS receiver. And there are many kinds of networks that can provide this sort of real-time signal. One of them is Wad Gps. This actually is used primarily for aircraft guidance. But as you see here, the concept is that there's a upload. You see that on the left with the yellow arrow going up. There's an upload to a satellite Inmarsat that then is used to broadcast these correction signals to aircraft. And then you see the GPS and GPS satellites that are also broadcasting the signals to the aircraft so that they get the GPS position and then corrected from the signal they receive from Wad GPS. And now here are some other wide area DGPS sort of beacons that can be used in the same manner. Here we have the Maritime DGPS Coast Guard system. We have the Wide Area Augmentation system. These are used more and more for precision agriculture, but still the system is fundamentally the same. The concept is that these are known positions that are continuously operating and recording the GPS constellation, and then that data is available using sometimes a real-time signal to be able to do a correction of a lone GPS receiver that is in an unknown position. And it isn't just restricted to the United States, this concept. EGNOS, Wide Area Network, is the European version of this sort of thing to actually cover the entire European Union. The Japanese are also planning a wide area augmentation system. This sort of real-time correction is getting more and more ubiquitous across the planet. Now, one thing that is worth knowing about this kind of correction is latency. It obviously takes some time for a base station to calculate its corrections. It takes some time to put it into data packets in the correct format and transmit them from the base to the rover. The data makes its way over the data link, either radio or cell phone modem or whatever is used at the rover. It's decoded. It must go through the rover software. All of this takes time. It can be as little as a quarter of a second or as long as a couple of seconds. And since the base station corrections are only accurate for the moment they were created, the base station must send a range rate correction along with them. And then the rover, using this correction, can backdate the correction to match the moment it was made at the base. It's interesting. What might not be immediately apparent is that it's necessary for the constellation to be the same at both ends of this line. In other words, at the base station and at the rover. They need to have satellites in common, of course at least 4 in common, so that the correction can be used by the rover. This sort of DGPS is very useful in GIS. As seen here, with a water sample being collected, and then the position at which it's being collected can be recorded with an electronic notebook, a pen computer, any number of data loggers. And it's possible, of course, to have these corrections in real time, as we've discussed, or it's possible to post-process after the work is over from continuously operating reference stations, base stations. For example, it's necessary frequently to return to a same site to perform inspections or maintenance. DGPS can allow you to do that, especially since you can get a real readout in real time. Now, obviously, one could do it autonomously with GPS without corrections, but the accuracy is much better if you have a real-time correction. Now, real-time kinematic. Well, generally speaking, this is used to differentiate this method from the pseudo-range or the code phase DGPS solution. Real-time kinematic is fundamentally the same, really. It is just that normally it's talking about carrier phase rather than just code phase. Here you see that its accuracy can be a couple of centimeters or so. And typically we say it must track 5 satellites minimum. The reason for the 5 satellites is basically to have one spare so that you're absolutely sure that you will have a position all the time. But the same concept is here. The base station, this would be set up at a known point, maybe an NGS brass cap. And then there'd be a transmission antenna associated with it, a radio transmitter. Then the rover would work at the unknown points and the real-time corrections would happen. Again, this is used for more accurate work. And notice that the baselines, in other words, the lines that can be occupied at this system, 10 to 20 kilometers, which is considerably shorter than DGPS's effective range. Of course, the difficulty with RTK, same as any kind of carrier phase solution, and that is integer ambiguity resolution. In other words, the determination of that ever elusive n, large N. Now, more and more equipment manufacturers have been able to find ways to resolve that carrier phase ambiguity very quickly. And dual frequency GPS certainly makes it easier to do that. If one is going to do this sort of work, it's necessary to have a radio license for broadcast. While these transmitters that are needed for RTK are portable, they still require licenses from FCC. And since it's true that voice communication is considered superior to data communication, it's always best to try to set your transmitter to a band that is not being overused in voice transmission. This is, of course, one reason why cell phones are being used more and more as an alternative radio link method in RTK. It does tend to ameliorate the signal interruptions that can occur over the radio link, and it has a somewhat wider effective range. Of course, as you well know, there are places where cell phones don't function well, and there are places where they do. Generally in developed areas, cell phones more and more are being used as the modem for RTK work. It's always a good idea, though, to have the transmitting antenna placed as high as possible for maximum coverage, so that one can go as far as possible. Generally, it develops that one of the limiting factors of RTK is the range of the transmitting antenna, or the transmitter, to send out the correction message. The fundamental idea behind both RTK and DGPS, the idea of a base station at a known position, is something that will carry over fairly consistently in both methods. As mentioned earlier, RTK is at its best under 20 kilometers, and the radio link gets troublesome usually before that limit's reached. Of course, it's vital that both the rover and the transmitter are at the same frequency. The data signal, the radio signal, can also be affected by atmosphere or refraction or reflection, even being too close together. It's interesting that here we have GPS that is really not affected so much by these sorts of difficulties, but the radio antenna in a real-time kinematic setup can be. And one of the things that's worthwhile to point out is in RTK, just as in all GPS, the fundamental coordinate is, of course, our centered Earth fixed XYZ. It has fundamentally ellipsoidal heights that will be derived from that position. However, of course, orthometric heights are the heights that are desired. So one of the things to take care with in RTK is to not confuse ellipsoidal heights and orthometric heights. Now, of course, it's quite possible to have a geoidal model in the data logger in doing RTK, or for that matter DGPS. But it's important to keep clear that that geoidal model is necessary in GPS if one is going to derive what is normally thought of as elevations or orthometric heights. In RTK, as for example in DGPS, the more satellites the better. The faster the integer ambiguities will be resolved in RTK. And it's not unusual to have 6 satellites above an observer's horizon most of the time. 8, even more. Now for baselines under 10 kilometers, an 8-satellite constellation should be very good for work under most circumstances. But of course, remember, PDOP and signal-to-noise ratio need to be considered. PDOP needs to be as small as possible. Signal-to-noise ratio needs to be as high as possible. Just a slide here about antenna heights, both at a base station and at a rover. This is one of the areas, height of instrument, or HI, where GPS surveys can go wrong. If one wants an accurate vertical position, it's important to know how high above the ground the antenna was at the time of the observation. Well, of course, having said all of this about the ease with which one can do single receiver differential GPS using base stations, it's important to remember that this does not change the fact that multipath can affect the results. The bounce that happens against buildings or other surfaces can cause the GPS position to be corrupted. Remember that we're determining distances to the satellites, and obviously if a signal bounces before it gets to the receiver, that distance is going to be incorrect. Also, if a GPS receiver is moving, a lock can be lost. Going under a bridge, under a tree, any kind of break in the signal can cause a cycle slip, loss of lock, and then of course once that happens it's necessary to reestablish that locked relationship with the signal coming in from the satellites. Now, generally speaking, it's a bit more difficult to do that with carrier phase observation than it is with code phase observations. And this DGPS has a clear advantage over RTK. Another technique that's interesting is that it's of course possible to set up a base station not immediately at a known position. Consider this. Let's suppose a base station was a base for several positions that were collected around it, but was not set up over an NGS known brass cap. Well, if that base station operated continuously, let's say for an 8-hour day, it would be possible then to go to the NGS CORS stations, continuously operating reference stations, download the data from those, and then post-process the base so that it would now be possible to derive a known position that that base had occupied all day. And then, in the next step, possible to determine the position of the rovers from the base. As mentioned earlier, there's more to know about the Rtcm correction. Here is a website in which you can learn more about it. There are new versions. One thing worth noting about the new versions is that the GNSS, meaning the additional constellations, not just GPS, but GLONASS and others that are to come, Galileo, for example, can be accommodating. The Rtcm can be accommodated by the new Rtcm. There's no question that RTK dominates GPS surveying applications in engineering, air navigation, etc. This centimeter level sort of real-time accuracy is used widely. The requirements of setting up a GPS base, though, with an RF transmitter and etc., has been seen as awkward and expensive. And the baseline of 10-20 kilometers for centimeter level work has been cumbersome to some, less flexible than many would like. And this has been one of the primary reasons that these real-time, continuously operating reference station networks are being created everywhere. Here's an example in Germany. Now, these stations, and you know they're available in the United States, form a network of bases that can be used to do such work without the investment in time and effort and money of having a base station of your own. There's no question that RTK dominates GPS surveying applications in engineering, air navigation, etc. This centimeter level sort of real-time accuracy is used widely. The requirements of setting up a GPS base, though, with an RF transmitter and etc., has been seen as awkward and expensive. And the baseline of 10-20 kilometers for centimeter level work has been cumbersome to some, less flexible than many would like. And this has been one of the primary reasons that these real-time, continuously operating reference station networks are being created everywhere. Here's an example in Germany. Now, these stations, and you know they're available in the United States, form a network of bases that can be used to do such work without the investment in time and effort and money of having a base station of your own. Now, these can be used in a post-processing approach, but more, we're seeing such networks as real-time networks. Governments and commercial interests are running these. Sometimes subscriptions are required for the real-time service. Sometimes they're free. In any case, there's a definite advantage in eliminating the individual base station preparations. These benefits, accomplished by services gleaning corrections of the whole network and then continuously operating stations, are combined into a correction. In other words, instead of doing a radial correction based on the base, then a single vector out to the unknown point, it's possible to take the entire network, download it to a central computer, at which a correction is generated for the entire figure, a model for the entire figure. Here's an example of what I mean. Let's suppose that these 4 reference stations all transmit their track GPS data to the data control center. And then this rover, in between the triangle that is generated by these 3, can have a differential correction sent to it from this data control center. Then that correction can take into account the corrections available on all 3 of these reference stations as a network, as a group. The central idea underlying Rtn Differential Correction is the combination of observations from several continuously operating reference stations at known positions to derive a model of the entire region. So rather than being considered isolated beacons, each covering its own segregated area, the cores are united into a network. The data from the network can then be used to produce a virtual model of the area of interest. From this model, distance-dependent biases such as ionosphere, troposphere, orbit errors, and you know what these are now, can be calculated. Once the roving receiver placed within that network is established, it's possible to predict the errors at that position. And not only can the cores network be used to model errors in a region more correctly, but a multi-base solution can improve redundancy. Solving several baselines that converge on the project point simultaneously rather than relying on just one, as a typical RTK setup does. Now, implementing such an RTN, a real-time network, means that there's an awful lot of data that has to be handled. It has to be communicated to a central computer, a data control center, and then the distance-dependent errors have to be calculated, and then the model sent back to the rover. Now, in this picture, what you see is an NMEA line going from the rover to the computer or the data control center. and then the Rtcm, which you know is the correction message going back. Now this NMEA string is actually telling the computer an approximate position of where that rover is in that triangle created by the reference stations. Finally, as it says, the pseudo-range or carrier phase residuals must be determined for the L1 and or L2 by using one of many techniques to interpolate the actual distance-dependent correction from the surveyor's particular position within the network. Then the subsequent corrections must be communicated to the surveyor in the field, which typically requires a large transmission of data. There's more than one way to do this. One approach is called VRS, or Virtual Reference Station, as you see here. This approach requires a two-way communication link. Users must send their approximate position to the Master Control Center via an NMEA string. This is a formatted string. And the Master Control Center returns the correction for an individual VRS via Rtcm. And then the baseline processing software inside the rover calculates its position using the VRS, the Virtual Reference Station, which seems to the receiver to be a single nearby reference station. This method is used widely, more and more, for real-time correction at the centimeter level inside a real-time network. And yet there's another version on the horizon that's very provocative, known as precise point positioning. And I give you a website down here at the bottom to learn more. As mentioned earlier, errors in satellite clocks and imperfect orbital information contribute substantial inaccuracies to GPS, especially in autonomous positioning, in other words, not differential, without the base. And the corrections available from the navigation message just aren't adequate. But positions several orders of magnitude better than the broadcast corrections can be achieved with this precise point positioning method. This technique utilizes precise GPS orbit and clock products available from international sources, we've talked some about that, to correct data collected by dual frequency receivers to ameliorate the ionospheric delay. Now, PPP is not a code-only solution, but relies on code and phase, carrier, in other words. The resources for the precise orbit and clocks include the IGS, JPL, and the National Resources Canada, NRCan, among others. There's an online service that will help users submit their collected GPS data over the Internet for PPP processing, and they can be returned in NAD83 or ITRF. Here is another service that makes it possible for a single GPS receiver to achieve good accuracy, and in this case, even done autonomously with high quality precise ephemeris and clock corrections, post-mission, post-processing. There's a lag time between the collection and the availability of the data, of course, but the advantages in this PPP approach is a single GPS receiver is all that's required. And of course that's the theme that runs through RTK, DGPS, and this, and that is that a single receiver can be used to achieve very good accuracy. So, here are some of the fundamental ideas that underlie GPS surveying. Most often, a fixed point with previously established coordinates is occupied by one receiver, a base. And this provides the data to compute the differences between its known position and the unknown positions measured at a second or roving receiver. Static GPS requires post-processing and is used to establish control. DGPS The corrections can either be applied post-processing or in real time. And while correlated systematic errors can be virtually eliminated with differential correction, the biases such as multipath and receiver noise aren't affected by that. These errors have much been reduced in modern GPS receivers, but not completely gone. Biases such as high PDOP can only be resolved with good receiver design and care when the surveying is done. The real-time kinematic is a method of choice for much GPS work, but the technique is being supported more and more by real-time networks and continuously operating reference stations. Then there's this precise point positioning. Offers centimeter, decimeter solutions that doesn't rely on differential correction, but rather on precise ephemerides and clock data. And all of these techniques are going to be improved even further by the Global Navigation Satellite System, or GNSS. And we'll talk more about that in subsequent lessons. Thank you for taking the time with me.